Welcome back, everyone, to MAE170. This is lecture 14 in week number 9. So today I want to talk about phase lead and phase lag compensators, but now seen in the frequency domain context. So what we will see is contained in chapter 10, and more specifically in chapter 10.3, 0.4, and 0.8. So as usual, we start by considering our closed loop control system. And we consider a phase lead or phase lag compensator, but we also allow for a constant gain to be varied. So we have K, and then we have our usual process or plant G of S. So here I'm proceeding parallelly to the left. We're going to describe the lead compensators, and to the right, the lag compensators. So if you remember the lead compensators, we are actually adding a zero, a real zero, at minus sigma z, and a real pole to the left of it, so at minus sigma p, so that sigma p in absolute value is greater than sigma z. And since we've defined alpha as the ratio between sigma p and sigma z, for lead compensators, alpha is greater than 1. And it's the other way. If we consider lag compensators, we have the pole that is closer to the 0, or to the imaginary axis. So, and then we have instead the real 0 that is to the left of it. So in this case, we have the sigma p in absolute value is less than the absolute value of sigma z. Therefore, the ratio alpha is less than 1. So these are things that we already know. Okay, so as I said, we're going to consider now the transfer function associated with the compensators, but we also allow a constant gain to be present, and this will be clear in a second. Now, since we're dealing with the frequency domain, we substitute S equals I omega. So we can rewrite GC with omega instead of S. So we have K times I omega plus sigma z over I omega plus sigma p. And we just collect sigma z at the numerator and sigma p at the denominator, so that we have 1 plus I over sigma z times omega, and at the denominator we have 1 plus I over sigma p times omega. What I'm doing here, I'm just rewriting the transfer function in the canonical form for the Bode plot. Now, sigma z over sigma p is 1 over alpha, so this becomes k over alpha. And then I'm also, just to follow the notation of your textbook, calling tau 1 over sigma p. So that is the characteristic time of your real pole, sigma p. So with that, we can rewrite the diffraction as 1 plus I omega tau alpha and 1 plus I omega tau. So the cutoff frequency associated with the real 0 is alpha times tau to the minus 1, and the cutoff frequency associated with the real pole is tau to the minus 1. All right, so let's take a look now at the limit for omega that tends to, either 0 or infinity when we draw the Bodhi plot, we have the x-axis containing the frequency to the very far left, where omega tends to 0, and to the far right, it tends to infinity. So let's take a look at the limit of this transfer function as omega first goes to 0, and then when omega tends to infinity. So we have to write the limit for omega that goes to 0 of k over alpha times 1 plus I omega tau alpha over 1 plus I omega tau. And so the limit is simply k over alpha for very low frequencies. For very high frequencies instead, well, what I want to do is just I collect omega on both the numerator and the denominator, so I can rewrite things as follows. 1 over omega plus I tau alpha, and at the denominator we have 1 over omega plus I tau. So omega and omega cancel. If omega tends to infinity, this tends to 0, and so does this term. Then I simplifies with I, tau simplifies with tau. So the result of the limit is k. Okay. Now, one thing that we want to do when we design a lead or lag compensator in the frequency system, so in the frequency response domain, we do not want to change the steady state response. So we do not want the transfer function to modify the steady state response. The steady state response is associated with what happens at low frequencies. So for omega that tends to 0. So if we don't want the transfer function of the compensator to influence what happens at low frequencies, it means that we want the limit for omega that goes to 0 of the transfer function itself to go to 1. And this is, so we want k over alpha to be equal to 1. So that implies that we want to get, or to pick, k equals alpha. So from a Bodhi plot perspective, this means that since GC of I omega for omega that tends to 0 is 1, when we take the logarithm, 20 logarithm of the magnitude, that it just goes to 0. So we're not increasing or decreasing the gain at very low frequencies. And we're also not adding any phase, because the phase associated with 1 is simply 0. So this concludes the fact, or with this, I can rewrite the transfer function for the compensators using k equals alpha, so that we're left with 1 plus I tau alpha omega over 1 plus I tau omega. So that is sort of the canonical way of writing the transfer function of a phase lead or a phase lag compensator in the frequency domain. Of course, if you wanted to write it down as a function of S, well, you can simply write what we started from, but now we know that k is equal to alpha, so GC of S is simply alpha times S plus sigma Z over S plus sigma P. where sigma p is 1 over tau, and sigma z is 1 over alpha times tau. So now let's actually verify that the steady state response does not change. And let's do that by considering the following example. So we consider a process with transfer function equal to n of s over s times d of s. So we're dealing with the system of type 1 because it has one pole at the origin. And then we consider an input 1 over s squared, so it's a ramp input. Let's now compute the steady state error for the uncompensated system. Here, of course, as you see, there's no compensator. We're just closing the loop with only the process. So let's see what is the uncompensated steady state error for such system. So by definition, the steady state error is the limit for s that goes to 0 of s times e of s. And so e of s, what is it? It is r times 1 over 1 plus g. So g in this case is n of s over s times d of s. So now substituting the fact that r of s is a ramp input, so it's 1 over s squared. S cancels with the square at the denominator. But then we rearrange this fraction. So we have at the numerator now s times d of s over s d of s plus n of s. So we have the other s canceling out. If we take now the limit for s that goes to 0, we're left with d evaluated at 0 over n evaluated at 0. So what I just found is the value of the steady state error for the uncompensated system. Now let's introduce our phase lead or phase lag compensator. And let's recompute the steady state error. Now, of course, the system is different because we do have a compensator. So now the steady state value of the error is, well, once again, s times r of s, which is 1 over s squared. But now we have 1 over 1 plus gc times g. What are we doing now is to substitute s equals I omega. So technically, we're switching our variable from s to omega. So if s goes to 0, then omega goes to 0. So we have 1 over I omega times 1 over 1 plus, then we can write our transfer function for the compensator as 1 plus I tau alpha over omega divided by 1 plus I tau omega. So this is the new thing. So this is our GC of I omega in the form that we found earlier, times n of I omega over I omega d I omega. Okay. So now if we take the limit and we rearrange things, we can rewrite this as 1 plus I tau omega times I omega times d evaluated at I omega And then 1 plus I tau omega I omega. Sorry, it's a little bit boring. Just rewriting things. Okay, so now we have this goes away with this. And so if omega goes to 0, we have this kind of goes away, this goes away. Actually, this whole thing goes away. This goes away. So we're left with exactly d evaluated at 0 over n evaluated at 0. So that is exactly the same steady state error for the uncompensated system. So in other words, as we already knew, but now we actually proved it, introducing a compensator, a lead compensator or a lag compensator written in this form does not alter the steady state response or steady state error of the system. So when we design a compensator in the frequency response domain, we don't really want to modify the steady state error, which is something a little bit different from what we've seen when we were designing especially the lag compensator in the root locus context, because we were designing the lag compensator on purpose to decrease the steady state error. In this case, we do not want to touch on the steady state error. We can use something else to control the steady state error. So the design of this phase lead or phase lag compensators their goal is going to be something a little bit different, as we will see. Okay, so once again, notice that as usual, maybe you haven't really thought about that, but when we compute the things in the steady state, in the steady state, yes, so the limit is calculated for s that goes to 0. So when we are instead in the omega domain, that is equivalent of having the frequency that goes to 0. So whenever we draw the Bodhi plot, things that happen to the very far left are equivalent to something that happens at the steady state response or error, whatever, the steady stateness of the system. All right, so now I want to draw the Bodhi plots in terms of magnitude and phase associated with the phase lead and lag compensators. So let's start with the phase lead to the left, and the phase lag is going to be to the right. I'm going to do things only for the phase lead compensator, and then you'll see things already completed for the phase lag. Nothing really changes much. Things are just flipped. So here we have that omega z is actually sigma z. So as defined before is 1 over alpha tau. And then we're going to introduce omega p. So the frequency associated with the real pole, or sigma p, is equal to 1 over tau. So for the phase lead compensator, we have that the frequency associated with the 0 is less than the frequency associated with the pole. And for the phase lag, we have the other way around. So the frequency associated with the 0 is greater than the frequency associated with the real pole. All right, so let's rewrite here the actual transfer function for the compensator. Actually, let me write it up here. So we have GC of I omega that is equal to 1 plus I tau alpha omega over 1 plus I tau omega. Okay. Actually, I'm going to do something a little bit different. I'm going to replace tau omega with omega z, or with 1 over omega z, and tau with 1 over omega p. So now it's clear that omega z and omega p are the cutoff frequencies for the zero and the pole of GC. Okay, so let's start by drawing the magnitude Bode plot for the zero. So it is 0 all the way to the cutoff frequency. Then at the cutoff frequency, we start raising our gain, and that will continue indefinitely. And the slope is plus 20 decibels per decade. What about the contribution of the pole? Well, that is 0 all the way to the cutoff frequency associated with the pole, which is omega p. And then after that, it starts decreasing with a constant slope of minus 20 decibels per decade. So now if we want to write, or to draw rather, the overall asymptotic curve, then that is 0 all the way until we hit omega z. Then we start going up following the dark green line because there's no contribution of the pole until we hit omega p. At that point, we start going down with the with minus 20 decibels per decade. So if we combine the upper slope with the lower slope, they cancel out. And so we end up with a flat asymptotic curve. Of course, if we want to draw the actual curve, we have to smooth things down. And so we're going to have something like this. Okay, so what is the value for the magnitude for very low frequencies? We already know, we responded to that question, and that is 0, and that matches. And what about for high frequencies? Well, let's go back. If we don't remember, we already took the limit, and that is equal to k, but k is equal to alpha. So for high frequencies, the magnitude tends to 20 logarithm of alpha. And since alpha for a phase lead compensator is greater than 1, logarithm of something that is greater than 1 is positive. So that matches perfectly what we were expecting. Now you see that I draw the actual curve so that it intersects the asymptotic curve at one specific frequency, that is halfway between omega z and omega p. Well, it's not really halfway, because remember here, when we draw the Bode plot, the scale is logarithmic. So omega m is actually the geometric mean between omega z and omega p. Or in other words, that is square root of omega z times omega p. And if we want to use alpha and tau, that is also equal to square root of 1 over alpha tau times 1 over tau. And so that is 1 over square root of alpha times tau. You see to the right, we have the Bode plot for a phase lag compensator. It is exactly the same, but now it's flipped with respect to the omega axis. And that makes sense because although at very low frequencies, the magnitude is 0, but for high frequencies, the value is still 20 logarithm of alpha, but for a phase lag compensator, alpha is less than 1. So the logarithm of a number that is less than 1 is negative. So the contribution gain-wise given by a lag compensator is negative for high frequencies. Actually, here in this box, I was going to write exactly this, so we can just drag this over here. So this is the geometric mean or average between omega z and omega p. Okay, so now we're ready also to draw the Bode plot for the phase. So in order to do that, let's start with the phase associated with the real zero. So we have that we need to center things around the cutoff frequency associated with such real zero, which is omega z. And then we have to consider 1 decade before and 1 decade after. So omega z over 10 and omega z times 10. Now the phase is 0 up to 1 decade before, and then we increase and we get to 90 1 decade after the cutoff frequency. It should be here. Oops. Okay, and then we stay at 90 for all frequencies that are above 1 decade after the cutoff frequency omega z. Now let's do the same for the phase associated with the real pole. So it's going to be 0 all the way to 1 decade before the cutoff frequency, and then it will settle at minus 90 after 1 decade with respect to omega p. So between those, we have the constant slope line over here. Now, if we want to draw now the overall contribution phase-wise of the lead compensator, then it's going to be 0 until omega z over 10. Then we just have the contribution due to the zero. And then when we arrive at omega p over 10, we have a plateau. And then the contribution of the 0 just remains constant, and we are decreasing following the fact that the contribution of the pole decreases until we hit 10 omega p, and then we are back at 0 because the plus 90 will cancel out with the minus 90. So now if we draw the actual phase curve, we have to smooth out things. And so we're going to be a little bit below the asymptotic curve. There we go. So you see now that we have a bump in the phase, not a bump in the face, but a bump in phase-wise. And that's exactly why this is called a phase lead compensator, because we're adding phase to our uncompensated system. That's exactly all this area below the curve. You see that we are adding phase, but we're adding phase only, it is only relevant between omega z over 10 and 10 times omega p. And as a matter of fact, we'll reach its maximum contribution at omega m. So at the geometric mean between omega z and omega p. Something similar can be said in terms of, for the lag compensator, we're actually removing or decreasing the phase once again between now omega p over 10, because omega p is lower than omega z, all the way to 10 times omega z. And the maximum amount of phase that we are subtracting is going to be in correspondence to omega m. Now, the amount of phase that we are subtracting, the maximum amount of phase that we are adding or subtracting, is going to be called phi m. And so for a lead compensator, phi m is going to be a positive number. And for a lag compensator, phi m is going to be a negative number. And you can find that this value is exactly arc sine, or sine to the minus 1, of alpha minus 1 over alpha plus 1. So obviously, if alpha is greater than 1, then you're going to get something positive. So arc sine of something positive is a positive number. So that's why phi m is positive. Vice versa, if alpha is less than 1, we're going to get a negative number. So, and that's why we're subtracting phase. All right, so how can we use the fact that we are adding or subtracting phase? Well, not only are we doing that, but if we're looking at the magnitude plot, we're also doing something else. We are raising the gain for high frequencies for the lead compensator, and we are lowering the gain when it comes to a lag compensator. So we can use these two facts, increasing or lowering the gain, or increasing or lowering the phase, to modify the response of our control system so that it will meet some desired requirements. So in the frequency domain, the typical requirements, remember before we were talking about percent overshoot, steady state error, rise time, so on and so forth. Here in the frequency domain, we have something a little bit different. And that's what we saw last time. That is the phase margin and the gain margin. And of course, the frequency associated with the phase margin, which is the crossover frequency. Then we can have requirements in terms of bandwidth or the zero frequency gain. So in other words, the magnitude of the Bodhi plot for omega that tends to zero. And sometimes this is also called the DC gain. And then we can also have requirements. This is something that we've already seen in terms of the steady state error. So now what I want to do is to present an example for a lead compensator design and then for a lag compensator design. But the problem is going to be the same. So we're going to have the same plant with the same requirements. So we just want to meet the same requirements using first a lead compensator and then a phase lag compensator. So you'll see that we're going to meet the requirements, but we're going to tackle the problem from two different points of view. All right, so here I'm going to consider a plant GS equals 1 over S times 1 plus 0.2 S. All right, so it's written in the canonical form for the Bodhi plot because we have the 1 plus tau S. And now the requirements are that the steady state error must be less or equal to 0.02 for what? Well, for a ramp input. And then we also want that the phase margin has to be greater than 48 degrees. Now, as I said earlier, the lead or lag compensators in the form that we chose, that is GC of S equals alpha times S plus sigma Z over S plus sigma P, these kind of compensators written in this way, they do not alter the steady state error or steady state response. So we have to take care of the steady state error first, so before designing the compensators. And that can be done by changing the gain, or let's see if we can do that. So here I'm also assuming that we have a constant gain that we can change. So let's say we have K, and then we have our plant, so 1 over S times 1 plus 0.2 S. So let's now compute the steady state error. So we have the limit of S that goes to 0 of S times R of S times 1 over 1 plus KGS. So that is S times, so R of S, since it's a ramp input, is once again, like we saw before, 1 over S squared times 1 over 1 plus K over S times 1 plus 0.2 S. So multiplying everything, denominator and numerator, by S times 1 plus 0.2 S, we have S times 1 plus 0.2 S over S times S. Okay, S and S go away. So if S goes to 0, then this goes to 0, this goes to 0. So we have 1 over K. And so we want this to be less or equal to 0.02. In other words, K has to be greater or equal to 50. So let's just select 50. So now we've modified the plant such that the requirements in terms of steady state error are met. So G of S is 50 over S times 1 plus 0.2 S. So you see that here we haven't started with the designing of a lead compensator or a lag compensator. We've just taken care of the steady state error. And let me repeat, and that is because the way the lead or lag compensators are written, they cannot modify the steady state error. So we have to find a way to modify the plant beforehand. Okay. So we only have one requirement to meet, and that is the phase margin has to be greater than 48 degrees. As usual, before designing anything, let's see if the uncompensated system actually already meets the requirements. Because if it does, there's no way, or it doesn't make any sense to design a further compensator. So let's compute the phase margin for the uncompensated system. So in order to do that, let's first draw the Bode plots, magnitude and phase for the modified plant. So we have G, and now we're considering I omega instead of S. So we have 50 over I omega times 1 plus 0.2 I omega. So here we have three components. We have a constant gain. So magnitude-wise, that's just 20 logarithm of 50, which is about 34 decibels. Then we have a pole at the origin. And finally, we have a real pole. And the real pole is characterized by a time constant of 0.2 seconds, which also means that its characteristic frequency or cutoff frequency is tau to the -1, so it is 5 radians per second. All right, so here I've already drawn the contribution of the single factors, so I'll just describe them, but you should already be familiar with them. The green line is just a constant line at 34 decibels, and that is the contribution of the constant gain. Then we have the contribution of the pole at the origin, which is a line with constant slope of minus 20 decibels per decade, and that intersects the 0 decibel line at 1 radians per second, so over here. And then finally, in orange, we have the contribution of the real pole. So the contribution of the real pole is, at least asymptotically, it is 0 up to the cutoff frequency, so up to 5, and then it decreases with constant slope of minus 20 decibels per decade. So now if we want to sum up the contribution of these three terms, we can first draw the asymptotic curve. So we have 0, 34, and then we add whatever. Let's start at 0.1. So, or actually, we can start at 0.05. And so at 0.05, the contribution of the light blue line would be 40. So you can actually, usually when you draw the Bode plots, you have a very fine scale graph paper, so you can draw things more properly. So anyway, here you see that the overall contribution, at least until we hit 5 radians per second, is just equal to the contribution of the pole at the origin raised by 34 decibels. So it means that instead of crossing the 0 line at 1 radian per second, we cross the 34 decibel line when we are at 1 radian per second. All right, so when we hit 5, now we have also the contribution of the real pole, so our slope increase or decreases further from -20 to -40 decibel per decade. All right, and so if we want to smooth down things, the actual plot looks, oops, well, this is not like this. All right, so this kind of looks like the, it should be the actual plot, similar to the actual plot. Okay, so this is in terms of magnitude. Now let's take a look at what happens at the phase. So here, once again, I've already drawn the contribution of the 3 terms for the phase. So 0 when it comes to the constant gain, constant -90 when it comes to the pole at the origin, and then we have 0 up to 1 decade before the cutoff frequency of the real pole, that is 0.5, and then it is -45 at the cutoff frequency, so at 5 radians per second, and then it reaches -90 and it stays there at 1 decade after the cutoff frequency, that is 50 radians per second. So if we sum up the contribution of all 3, we're going to be at -90 until we hit 0.5, and then we start decreasing and we hit -135, which is -90 -45, and then we settle when we reach 50 at -180. So smoothing things out, we obtain an actual plot that sort of looks like this. All right, very good. So now let's see, at least graphically speaking, where the phase margin and the gain margins are. Well, we're only interested in the phase margin. So the phase margin is the difference between the actual curve and -180. So this bit here is our phase margin. And that happens in correspondence to the crossover frequency. So actually, I should have done the other way around. I should have looked when the magnitude plot crossed the 0 decibel line, which happens about here. So we don't know the value of the crossover frequency yet. We just know that it's more likely greater than 10 if we drew things properly. And so in correspondence to such frequency, we just take a look at where the phase of our actual plot is, and the difference between that point and the -180 degrees line is going to be our phase margin. So we can see here already graphically that our phase margin is less than 48 degrees, and that is because this distance over here is 45 degrees. So we know that we need a compensator to increase our phase margin. But let's actually compute the phase margin. So by definition, what we saw last time, that is the phase of our, in this case, uncompensated system, plus 180. So remember that here, although we are considering the closed loop system, we want to take a look at the loop transfer function. Remember that we were considering L of I omega, and L is the transfer function on the upper branch of in our block diagram. So in our block diagram now, for the uncompensated system, L of S is equal to 50 over, what was it, S times 1 plus 0.2 S, okay? All right, so here I'll spare you with the details for the calculations, because we've already seen a similar example last time. So here I'm just computing first the crossover frequency, because that's what we need. So the crossover frequency is the frequency such that the magnitude of the loop transfer function is 1, or when we take 20 logarithm of that, that is 0 decibels. So we're just doing exactly what we saw last time, and we're solving for omega. In this case, we end up with an equation of fourth order. So once again, we can use the Newton's method, and we find, after 4 iterations, that the crossover frequency is 15.42 radians per second. So our crossover frequency is 15.42. So let's go up and write that number. So yeah, it makes sense. So it means that our plot is pretty accurate. So if you draw things accurately enough, then you already have an idea of where your crossover frequency should be. So, and that you need that because when you apply the Newton's method, you need the first guess. So here in this case, I used 11 radians per second. Why did I use 11? Because I knew that the crossover frequency had to be greater than 10. So I just used 11. All right, so now if we compute the phase of our G transfer function at omega c, well, what is that? It's minus our tangent of omega c over 0, which is minus 90, and then minus our tangent of 0.2 omega over 1. So if you substitute omega c in that, you find that this is about minus 72. So the phase at the crossover frequency is minus 162 degrees. Does that make sense? Let's go up and see. Well, yeah, that makes sense. So this should be minus 162 degrees. So what is the phase margin that we actually have? The phase margin is minus 162 plus 180. So it is 18 degrees. And 18 is obviously less than the requirement of 48 that we had. So what we need is to add at least 30 degrees where at the crossover frequency. So we can think about using a phase lead compensator because that's what the phase lead compensator does. It adds phase. And here we have to add about 30 degrees of phase. So why not using that? So we have already the amount of phase that we want to add, phi m. However, there's a small problem here because the lead compensator, and we should go back to where we drew the Bode plots for the lead compensator. So not only do we have an increase in phase, and this is what we are looking at, we also have a side effect in terms of the magnitude, and that is we're raising the magnitude, and not just for very high frequencies, but that happens also where we add the phase. So if we want to add a maximum of phase of 30 degrees at our crossover frequency, we're also increasing the gain, and that means that we're actually shifting the new crossover frequency to the right, because now the overall system intersection with the 0 decibels will be shifted to the right. So the new crossover frequency will be larger than 15.42. So I'm saying this because it's not going to be enough to add just 30 degrees, because you're adding 30 degrees at an old crossover frequency, but we're going to have a new crossover frequency. We don't really know where that is until after we added the phase lead compensator. So what you should do is to add a sort of a safety phase, and you can add maybe a 15 degrees so that you have an overall maximum addition of 45 degrees. So this is the actual phase that we want to add at our old omega C. Also, there's another thing that you should keep in mind is that there's no one single phase lead compensator or phase lag compensator cannot add or subtract more than about 55 degrees. That is the practical limit. So if you wanted to add or remove more than that, then you should cascade or put in series more than one compensator. All right. So anyway, here we've determined that we want to add about 45 degrees in terms of phase. So our compensator is, as usual, 1 plus I omega tau alpha over 1 plus I omega tau. And so to design the compensator means that we actually have to find the values for tau and for alpha. How do we do that? Well, we already know that we want to add the maximum of the phase at our old crossover frequency. So the maximum of the phase happens at omega m. So we equate omega m with omega c. And remember, omega m was 1 over square root of alpha times tau. And so that is equal to the old crossover frequency, uncompensated crossover frequency of 15.42. But we need another equation because we only have one equation in two unknowns. And the other equation comes from the maximum of the added phase itself, which is phi m. And that depends solely on alpha. Remember, that is the arc sine of alpha minus 1 over alpha plus 1, and we want this to be equal to 45. So we have that sine of 45 has to be equal to alpha minus 1 over alpha plus 1, or square root of 2 over 2, which is sine of 45, equals to alpha minus 1 over alpha plus 1. And so we have that alpha is 2 plus square root of 2 over 2 minus square root of 2, which is about 5.83. And I can round it up to 6 to be a little more safe. And once again, when you compute alpha, you always want to check that is greater than 1, because otherwise you've done something wrong. You always expect alpha to be greater than 1 for a phase lead compensator. So now that we know alpha, we can use 1 over square root of alpha times tau equals 15.42 to find that tau. And now, of course, here we are substituting 6, or square root of 6. So tau is 0.0265 seconds, and alpha times tau is 0.1589 seconds. And so we can find that sigma p is equal to 1 over tau, which is 37.74 radians per second, and sigma z, or remember sigma p is also equal to omega p, and sigma z is equal to our omega z, 1 over alpha tau, and that is 6.29 radians per second. So the frequency associated with the 0 is lower than the frequency associated with the pole. Everything checks. So we are actually dealing with the phase lead compensator. So now we can draw the Bode plots magnitude-wise and phase-wise for the compensated system and compare it to the uncompensated system and see how things have changed. So here I already have the things drawn. So you see that when it comes to the magnitude, as predicted, we are raising the magnitude after the crossover frequency, and then we have, a little bit this region, the amount of gain added is not constant, but it becomes constant for high frequencies, and that is exactly 20 logarithm of alpha, that is 15.6 decibels. 20 logarithm of alpha, in this case, is 20 logarithm of 6, which is 15.6 decibels. So at high frequencies, our gain has been raised by 15.6. However, our gain is also raised at our crossover frequency, at old crossover frequency, so that our new crossover frequency has shifted to the right. So our new crossover frequency has actually shifted by quite a lot. And you can find it using MATLAB, because that becomes a little bit cumbersome doing it analytically. And that is 30.9 radians per second. So we've doubled it. However, that is just the side effect, because what we really wanted to do is to add the phase. So we're adding a bunch of phase in a spectrum of frequency, and the maximum of phase that we've added was corresponding to our old crossover frequency. However, we want the phase margin to be greater than 48 at our new crossover frequency, because that's where the phase margin is defined. We have to define the crossover frequency, 30.9, follow it all the way down until we hit the phase of our compensated system, and see if our new phase margin is actually greater than our requirement. So once again, here I've used MATLAB to do so. So you can follow the instructions that I told you last time. So you right click on the plot, select characteristics, and then phase margins or all margins. So you'll see that the new crossover frequency once again is 30.9 radians per second, and the new phase margin is 48.3 degrees, which is indeed greater than 48. So we've met the requirement. Just barely though. So we really needed those two safety precautions that we chose, that is that extra 15 degrees and also rounding up alpha to a slightly higher number. Okay, so let's recap what we've done using a phase lead compensator in the frequency domain. What you do is you actively increase the phase. However, the side effect is that you shift the crossover frequency to higher frequencies. And you also have an increase in the high frequency gain by 20 logarithm of alpha, which in our example, once again, was 15.6 decibels. So our compensated system, if we want to write it down in the block diagram form, is, so we have the block for the compensator, 1 plus 0.1589 times S over 1 plus 0.0265 S. And then we have the plant. So we had that constant gain that we added in order to meet the steady state error requirement. And then times the old plant, which was 1 over S times 1 plus 0.2 S. And you can also, what you can do is you can plot the steady state error for a ramp input, and then you'll see that the steady state error has not been affected. All right, so I'm gonna stop this video here, and then I'm gonna just do a shorter second video in which we see the same problem, but with the design for a phase lag compensator. So I'll see you in video number 2.